Okay, in this sample problem here, you're given a wire that's bent in this form. It's got uniform linear charge density, lambda, that's constant. And you need to find the electric potential at this point, O. Right? So you've got 3 different parts to this wire. This is the first segment, number 1, this is the second segment, and this is the third segment. So the potential at O, I've tried to break it up and call this V1, potential due to this here as V1, and then V2 is the semicircular part, and V3 is from the other straight part, right? Since these two, number 1 and number 3, these are both of the same length, 2r, and same distance to the point O, contributions, V1 and V3 will be the same. So we just need to calculate one of them and then calculate the V due to the semicircle, right? So let's do that. So V1 is equal to, I have to pick a dq. So say this is your dq, right? That's dq. And V1 will be integral ke dq divided by r, where r is the distance of the point from q. So this distance is your r. And I need to take a coordinate system to be able to do this. So let's say this is x equals 0 here. I'll put it at one end of the rod, x equals 0. This end of the rod here is x equals 2r. And then point O is at x equals 3r. Right? And dq is at position x, and its length is dx. So all of this is just like what you used to do. dq is lambda times dx. And your distance, r, is the whole distance, 3r minus x. You see? So with all that, if I go back and substitute here, I have integral ke dq is lambda times dx, because it's a straight wire. And then little r is 3 capital R minus x, right? And x is going from x equals 0 to x equals 2r. So I can simplify this. I can say this is ke lambda, and you could do a substitution if you like. 3r minus x is u, then dx will be negative du. So this ends up being negative a negative du over u, so it's negative natural log of u, and u is 3r minus x, right? So that's what you would get for integrating this, and that's to be evaluated between 0 and 2r. Okay, so if I simplify this, I have it to be ke lambda times negative natural log of 3r minus 2r, that's just r, minus of minus natural log of when x is 0. When x is 0, this is just natural log of 3r. Right? So I can simplify this. I can actually leave it like this, but we can simplify a little bit so it looks cleaner. So it's ke times lambda, and this I can simplify as natural log of 3r divided by r. Right? So the r goes off. So this is ke lambda times natural log of 3. Right? So that's your V1, but it's also same as V3. Right? So we've got those two parts. We calculated this, and now just have to calculate the semicircular part. Right? So very similar to what we have done with the electric field ideas, right? So with the semicircular one, you pick a dq. Let's say this is dq, and little r is equal to capital R, right? So I want my V2, that's equal to integral ke dq divided by r. I can simplify this. This will be integral ke lambda dl. Remember, that is So I need some theta here. So perhaps I can call this theta here. I can call this theta. So it's Ke, and then d theta is the angle that it subtends, right? So Ke dq is lambda dl, but dl is r d theta divided by r, and r is capital R here. Right? That's what you have. And theta goes from 0 to pi, right? 0 to pi. So if I simplify this, well, r goes away. Ke times lambda, those are constants. Ke lambda. And then integral d theta is just theta to be evaluated between 0 and pi. So that's just pi. Okay, so that was a lot simpler than I thought. So what I have is now I have V1, V3, and V2. I just have to add them up to get the total V, right? So substituting all of this in here, I can say my V is equal to V1 and V3 are the same. So it's 2 times this. So it's 2 times Ke lambda times natural log 3 plus Ke times lambda pi, right? Or I can clean it up a little bit. Ke lambda times 2 natural log of 3, or I could have said natural log of 9, right? 3 squared plus pi. Okay, so yeah, let me write it. Ke lambda times natural log of 3 squared, or 9 plus pi. Okay, so that is the electric potential due to this shaped wire, right? Charged wire.